All right, so today is going to be relaxing, nice relaxing Friday, because this is all review. In fact, you've already used this thermochemistry stuff in your lab when y'all did the combustion analysis stuff, so you did products minus reactants and everything like that. Hey, we tried to wait as long as we could. You missed our chat GPT joke. So we're going to start that now, asking the AI for a joke. It wasn't a great joke, so don't worry. You didn't really miss out. And so the thermochemistry, this is what you're, I guess, familiar with mostly, is like delta H of reaction, delta G of reaction, looking into the thermodynamics of chemical reactions and phase changes. So this will introduce the energy that is put in or released by phase changes, and then that will lead into phase diagrams, which is our next part of the course. Now we have a couple of different standard conditions. So this is the standard condition when you see the little degree symbol here. And so whenever you see this up here, both of these little superscript zeros, that's 298.15 Kelvin in 1 bar. It always irritates me that it's bar whenever we use atmospheres for everything, and then, so. And so then, let's see, 1 atmosphere. Yeah. So 1 ATM is equal to 1.01325 bar. Do you recognize that number? Yeah, it's one of the conversions.
Is that one of the values for R?
It was when we did the ratio of R's. Remember, we did the ratio of the joules per mole Kelvin divided by the atmospheres per mole Kelvin, and that's because 1 atmosphere is equal to 101,325 pascals. And so 1 bar, for some reason they didn't like that, which I don't know why. That's just the definition of atmospheres. So 1 bar is equal to 100,000 pascals. Yeah. So that's where bar came from. It's just they consider it more SI than atmospheres. But they're both defined regarding the Pascal, and so I don't know. But why fight it? That's just what it is. So that's our standard temperature and pressure. Notice it's standard, we call it standard ambient temperature and pressure. So this would be called SATP. So SATP. STP is equal to 1 atmosphere and 273 Kelvin, which is ice water. So STP we talked about when we covered the ideal gas law and gases in the freshman course, and then I guess we probably talked about it in this course as well. But it was one of the first standard conditions because they could make ice water very easily. And so if you're measuring volumes of this, you mix a certain volume of 2 reactants together, stick it in ice water, and you can see the volume change because it's at a constant temperature. So your standard constant pressure, constant temperature, you can see the changes in volume. So, okay, let's talk about phase changes. So we have vaporization and fusion and sublimation. Now this is a really strange, I don't know where this comes from, but ancient days, that's what they called this melting and freezing. They called it fusion. Okay. Now we have a totally different definition of fusion. But when you see the delta H of fusion, sometimes people write the fusion in front, like with the delta. Other times they write it like this. And so that's going to be the melting of the solid. So when it's melting, that's going to be called fusion. It is always backwards in my mind. To me, when you're fusing something, you're bringing two things together, like fusion of nuclei. It's exactly the opposite here. And I think It probably dates back to, like if you make a sodium chloride fusion, it's molten sodium chloride. And so they're melting that sodium chloride, and you can dissolve your analyte in that and then let it solidify, and then you can analyze it like in the infrared. So that's just, anyway, it goes way back. Boiling and condensation, no question there. The VAP for vaporization. Why did they start showing up in front of the H's in terms of after the H's? I think that's because of Atkins. So that was his influence. They were always after the H, and then Atkins started putting them in front. That was his preference in all of his books. And then sublimation, going straight from solid to gas. Now, it can also be measured directly, or it's the sum of both the vaporization and the fusion delta H's. So we can show this in a diagram. So over here, in terms of enthalpy, we can think of the average energies of these systems and draw a line. Just like, when we did for quantum mechanics, we had all of these, energy levels, and we did the probabilities of each one, and we had the energy of each one. And we multiplied those together, added them together, and that gave us the average energy. And so then this right here would be the average energy or average enthalpy for, say the reactants, right? And then, so that's say the solid, then we melt it. So this would be the solid, this is the liquid, and this is the gas. So this is the fusion enthalpy, this is the vaporization enthalpy. You add those together, you can get the sublimation enthalpy. So you can go from the solid directly to the gas. If you reverse the process, you just reverse the arrows. So you're already familiar with energy level diagrams, but now instead of individual quantized states, we've got moles of molecules. I mean, there's just, there's 10 to the 23rd molecules, and then you've got 10 to the 30 or 40 states if it's a gas, probably a comparable amount if it's a liquid and a solid, because even though you lose translation, you gain, what you lose in translation, you gain in vibration. So you could think of this tabletop as one giant molecule that's really not uniform. But if it's got, we'll just say, 10 to the 23rd atoms, you've got 3 times that many, so 3n minus 6 vibrations in the tabletop. So it's like, in terms of its degrees of freedom, that's how many vibrations it would have. So you take away all those translations because the table's not running around the room. It still has 3 though, X, Y, and Z. It has rotations, you still have 3 rotations, but in terms of all of those translations, the degrees of freedom of independent atoms, now it's combined into one substance, and you have that many vibrational modes. Okay? And many of those are really low energy because the whole bending of the table, is very easy compared to the stretch of a bond. So we average all of that out to an enthalpy for that tabletop, and then we just draw a line at that energy. Okay. So we do need some standard states, like where, do we set this at 0? Remember, we always had our ground state set at 0. So I can put a question mark there, right? Is this where 0 is, or is 0 up here? Where do we put 0? In our quantum mechanics case, it was easy. It was the ground state. Where's the ground state here, right? So that's where we need some definitions. And so here's the standard definition for enthalpy. Pure unmixed reactants in their standard states becoming pure unmixed products in their standard states. And so this is the delta H of reaction. And so this is sort of the standard definition for reaction enthalpy. And so we have our products added together, all the enthalpies of the products, and subtract the enthalpies of the reactants. We take into account the number of moles here and the number of species and so on. And so here's an example, this generic equation, 2A plus B gives 3C plus D. So we have 3 moles times the enthalpy of C 1 mole times the enthalpy of D, because that's the products, and subtract 2 moles of the enthalpy of A, and 1 mole times the enthalpy of B. So, oops, that should be a minus sign, shouldn't it? Or no, I've got the brackets. Yeah, I've got all in brackets. So. And so then this enthalpy of A is the standard enthalpy of each species in kilojoules per mole. So what do we mean by these standard enthalpies? We've got to have some way of picking 0 and then sorting all the others. And so let's look at a couple of ramifications of that. So here's an example where if we set the enthalpy of the elements at 0, then we could calculate the enthalpy of formation of this substance. So we're forming NH3 from elements. And we'll see later that that is the definition. The elements in their standard states we've set to 0. So it's kind of strange. We want to form 1 mole of ammonia. So we want to think about just forming 1 mole of ammonia. Well, that's a little difficult to do using elements in their standard states, because nitrogen is N2 and hydrogen is H2. And so how do you get 3 H's out of pairs of molecules, right? So you take those pairs, divide them by 2, and then multiply by 3. So we have 3/2 moles of H2 and 1/2 of a mole of N2. If we tear those bonds apart, so we had like the molar enthalpy change of tearing the hydrogen apart, we divide that number by 2 and multiply it by 3, and then add that to 1/2 of the molar enthalpy of N2, that bond, then that's this many joules. So that has torn everything apart to atoms, free atoms. And then so this is also just showing that we can add all of these individual reactions together to get the resulting reaction. And so let's say we don't know this number here, but we know somehow all the individual bond energies in the ammonia molecule. So we have free atoms. Look what we've made. We've made an NH molecule. And that was the bond energy for the first NH. Then this is the bond energy for the second NH. And then this is the bond energy for that third NH. And now we have NH3. When we form those bonds, they release energy. Okay, so this is going down. So this is a negative number. If we're going down, I'm going to mark out that little head up on top. And this is a negative number if we're going down. And this is a negative number if we're going down. So we have a plus this for tearing apart the reactants. And we have all of these numbers here. We add those together and we get the difference of minus 45.9 times 10 to the third joules. Any questions on that? Pretty straightforward. And this is with the 0 point here with elements in their standard states. Notice the 0 point is not the free atoms. That was just a decision the scientific community made. Okay. Now, a different scientific community developed Gaussian. Okay. Well, let's go ahead and start talking about this. So that standard enthalpy of formation, which we just saw, is the standard reaction enthalpy for the formation of the compound right here from the elements in their standard states. It's the most stable state at 298 and 1 bar. So we call that 0 for the elements. And so that was what that N2, that 1/2 N2, and the 3/2 H2 was referring to. Those were both the elements in their reference states, which is their standard or more stable state at 1 bar and room temperature. So now we have this concept defined, this delta HF. So we can go through and we can, now that we have a 0 on our vertical scale, we can compare everything to the elements in their standard states. And so some enthalpies, compounds, enthalpy of formations will be positive, meaning they're kind of uphill thermodynamically from their elements, and it would be stable for those molecules to fall apart. It would be exothermic if they fell apart. Things like water are downhill from hydrogen and oxygen. So if you were to tear water apart into hydrogen and oxygen, you had to put in energy to break apart those bonds. If you have hydrogen and oxygen, you mix those together with a spark, it will produce water and give off a lot of heat. So there'll be exothermic to form that. So you can just look at the table to kind of see which things are more stable or less stable than their elements. And so now a different community developed Gaussian, and they have a different reference state. So Gaussian does not compare everything to the elements in their standard states. Gaussian compares everything to completely separated nuclei and electrons. So look at that up there. That's crazy. An N7 plus. Okay. And 3 H pluses and 10 electrons at infinite distance. So that you don't have the Coulombic attraction, of the electrons to the nuclei, or the Coulombic repulsion of the nuclei from each other, and so on. So basically, that would be 0 Hartrees. So if you were to do a calculation somehow of just a proton or an electron or whatever, it's not associated with anything, and so it would give you 0 Hartrees. If you bring an electron and a proton together, where they join together and form a hydrogen atom, then that's going to be negative, right? Because you have the attractive forces of the electron and the proton. So this is nice. It's a nice reference state because everything is negative from this point. This is as high energy as you can go. It's to strip all of the electrons off of all of the atoms. Okay. And I would say it's the highest you can go in terms of chemistry. Now, physics could go higher. Physics could pull the nuclei apart and have protons and neutrons and electrons. But chemists developed this program, and it's interesting for chemists calculating chemistry. We can't do nuclear things with Gaussian, but we can do chemical things with Gaussian. Okay. And then where would the physicists stop? Would they pull the nucleus apart to protons and neutrons, or would they tear those apart to quarks? And then when we get to muons and gluons and all of that stuff, I mean, where does it end, right? So this is a nice stopping point. We'll just pull the electrons off and we'll sit there and call that 0. And then even if we make a hydrogen atom, it'll be negative. And so all your energies in Gaussian are negative for that reason. You noticed how all the energies came out negative. Okay. And so we could do the same kind of thing. We could calculate all of these. We could calculate the uphill of stripping all the electrons and everything off of our nitrogen and hydrogen, and then we could calculate the bringing everything together to make ammonia, and we could take the difference between these two. So here, this difference is negative 296, 685 kilojoules. That's an enormously negative thing because we've made a couple of stable molecules. And notice the numbers here. I've taken this is the hydrogen atom energy, enthalpy, and I've multiplied that by 3. And here's the nitrogen. So I add all those together, and I get this many Hartrees, and it's like 2,565 kilojoules per mole per Hartree. So that's what we get for those. And then over here, this is the energy in Hartrees of the ammonia molecule. And if I take the difference between these two, I get 45.9. So that's pretty good. So Gaussian is a darn good program. It can reproduce a lot of these thermodynamic properties. And so this enthalpy of formation of hexane can be used and can be found in bomb calorimetry. And so here's an example of using bomb calorimetry to calculate the enthalpy of formation. And so if we certainly know the enthalpy of formation of CO2. So we've got that one. We know water. Oxygen is going to be equal to 0. Enthalpy of formation for oxygen is 0 because it's an element in its standard state. And so we can look at this. This is the combustion reaction. Hexane plus oxygen forms CO2 and water. We can measure the enthalpy of combustion from bomb calorimetry. We put in all of these numbers and then we solve for this one. This is the unknown right here. So doing this with all the combustible substances, we were able to calculate these enthalpies of formation for a lot of different substances. And so here are some enthalpies of formation that I've shown. And I put a variety in here. Here's ammonia. It was 49. I don't know what the difference is between that number and this one, 46. If you look in the literature for these things, they're determined with different methods. And you go to Chemistry Web Book and you look up ammonia and go to the thermochemistry data, they'll have a table with reported values from the literature, and then like maybe 49 or 46 and so on. So there's some disagreement sometimes between tables as to which one they're using. So that's where you just end up citing your sources. Where'd you get this number? So it's not a huge difference. But then we have, this is hydrogen peroxide, here's water, here's sodium chloride and potassium chloride. So these are all negative, which indicates that they're exothermic in their formation, meaning if you take the elements and bring them together, then they're going to give off energy when they form these compounds. Look up here, these are positive with respect to their elements. So N2O4, NO2, and N2H4, these are all positive with respect to their elements. So if you were to somehow put those compounds in an environment where they could rearrange, they would rearrange to nitrogen and oxygen, okay, or nitrogen and hydrogen. So let's do that. Let's calculate some of these. So let's take hydrazine, which was one of the original rocket fuels. It's still used today in some sort of advanced hobby rocket fuels. So how do we calculate this? We've got products minus reactants, so we've got 2 moles. I've simplified the number of significant figures over here. So here's our water, 286. Yeah, 286. 2 times 286. And then we want to subtract the reactants. Oxygen is 0. And so the hydrogen is a plus 51. So if someone could do that for me on their calculator. That's 560. 72, 572, 623, 621, 520, okay. Is 520 or 620?
520.
Kilojoules per mole. Well, we put in the mole, so it's just kilojoules. So 521 kilojoules. So that's pretty good enthalpy of combustion, or reaction, if you will. But it's kind of a problem because we have a gaseous reactant. And so when you're making your rocket and you got to put as much fuel on board as you can, having a gas is a difficult thing because it's not very dense. Do you recall, or maybe you can calculate, let's think about this. So one mole of a gas is how many liters? 24? Yeah, so 24 liters. So think about a 2-liter Coke bottle, okay? You got, what is that, 12 of those. So 12 2-liter Coke bottles. That's 1 mole of gas. What is 1 mole of water? Let's just pick water because we know its density. Liquid water. So that's 18 grams. And how much volume per gram? What's the density? One. So 1 mil. So it'd be 18 milliliters. Okay, 0.018 liters for liquid water. And the liquids, maybe a hydrocarbon is going to be maybe 60% or 70% of that. So it's going to be really small. So the gases are about 1,000 times, more volume than liquids for the same mass. So let's try to put a liquid oxidant in there. So here's peroxide. And so let's see what we get with peroxide. This changes the number of moles of water. We still have nitrogen, though, as an element, so that's 0. 4 times 286. And then we're going to subtract 2 times the peroxide, which is 188, negative 188. And then we're going to subtract 1 times the 51. So don't drop your negative here. So again, your products are positive, your reactants are negative, you add them all up. It makes sense because you're taking apart your reactant, so you're going to change the sign and then add all those up. $8.19. That's fantastic. Not only do we have a more dense situation, we can make a smaller rocket, one that doesn't have a huge compression tank on it. We can use a thin-walled tank to hold the liquid peroxide. We pump that peroxide in and join it with hydrazine, and so we have an H2O2 tank and a hydrazine tank, N2OH4. And so we have these 2 tanks. We pump that in here. We pump this one in here. We get them close to each other. We add a little spark. And then we put it in a parabolic reflector. What does that do for us? So if your explosion is going on right here, what happens when the gas explodes? It goes in all directions, right? Kind of like a light source. And the parabolic reflector takes all of these rays and makes them collimated. If you're at the focal point of a parabola, everything that hits is going in one direction. So that's why the shape of those rocket engines are what they are. And so you've heard the phrase, well, it's not rocket science. Well, this time it is. Right? So you put that exothermic source at the focal point of a parabola and collimate the force in one direction. There's going to be an equal opposite force in the other direction. It's going to push that rocket in one direction. We could, just because hydrazine is uphill from its elements, we could just not even need an oxidizer. We could just spark the hydrazine by itself and not even need to take the oxidant. And so in this case, we have 0 for the products, and we have a minus 51. Okay. So that equals minus 51 kilojoules. If we just spark the hydrazine in a parabola, it will decompose and make oxygen and hydrogen, and will push things. And so that's what we have for our little positioning rockets. If you've ever seen those, and you can see them on the latest Falcon rockets when they come back in. So they're falling this way, and then you see this little flame come out of the side of the rocket, normally on the bottom side, so it tilts it up. And so those positioning blasts, a lot of times, I don't know if that one particularly is hydrazine, but it's a compact fuel doesn't need an oxidizer, very easily to control. All you need is a spark. So you open the valve, it's pressurized, open the valve, it sprays out, you spark it, it decomposes and pushes. Okay. Now we can do the same thing for Gibbs energy. So if we say that the elements, the Gibbs energy of the elements in their reference states is 0, then we can make tables of the Gibbs energy. And we've done that as well. So that's where these tables come from here. And this is the table that you'll have on the exam. You have the delta H, the delta G, both the formation of all these substances, and then the standard entropy. Now the standard entropy does not have the same reference state. What is the reference state for entropy? It's a bit of a review question. It wasn't in today's notes. It was 2 or 3 lectures ago at least. So the first law of let's go 0th law, let's review quick. 0th law is defining what? Temperature, right? So any two substances or property, any two systems in thermal equilibrium share a property. That property is temperature. First law of thermodynamics, energy can be created or destroyed, and then they added mass energy because of Einstein's law. Okay, so that's the first law. Second law, entropy of the entropy of a spontaneous process in an isolated system is increasing. Yeah. And then the third law, that's the one that defines the reference state for entropy. So it says as temperature goes to 0, entropy goes where? As temperature goes to 0, it can. You got 2 choices, right? Does it go to infinity or go to 0? Think about your partition function. As temperature goes to 0, the partition function goes to 1, right? Because it goes to the ground state. And the partition function is how many levels are populated. So if everything goes to the ground state, you have 1 level populated. And that is an entropy of 0, because entropy is the natural log of the partition function. So natural log of 1 is 0. So that's probably the best definition of the third law of thermodynamics. As temperature goes to 0, the partition function goes to 1, and entropy is K times the log of the partition function. So S goes to 0 as temperature goes to 0. Now, the other thing, too, is just to always think that entropy and temperature go with each other. So if temperature goes up, entropy goes up, because you're populating more energy levels. When they talk about entropy as a tendency towards disorder, that's the layman's term, the man on the street term for populating more energy levels, right? Because that's disordered. You know, if we came in here and there were only 6 seats, there'd only be one way for you guys to sit. I mean, maybe you could figure out how many permutations there were of you being in seat number 1 or seat number 2 and so on. But if there's now 22 seats, you have more options. And that is what entropy is talking about, the quantum options. Okay, so let's consider this situation where we have a really, really large Gibbs energy. So we can look up this Gibbs energy in the table. This is a different reaction than what's in your notes. So if you're looking at that going, wait a second, I'm trying to find one with a really spontaneous Gibbs energy. And this is a pretty big one, oxygen and aluminum. So we have oxygen here. This is going to be a 0 Gibbs energy. Aluminum is not listed in the table, but it's an element. It's a solid at 1 atmosphere or 1 bar in room temperature, so it has 0 here. 0, 0. And then aluminum is minus 1582 kilojoules. It's 1 mole times that, so it's kilojoules. And so this is our Gibbs energy for this reaction. Now, we developed earlier that the equilibrium constant was that minus delta D over RT. That's familiar, right? Okay. And so these are the numbers. You have so getting into joules, because that's what our gas constant is in joules. This is 1,582,000 joules, okay, per mole. So the per moles cancel, the joules cancel. So our exponent should be unitless, and it is. So all of these units are gone. The minus signs even cancel. Okay, and so we have an e to a huge number, 638. Now, I was trying to find a number that was big enough that would give an error on the calculators, but on my phone, my calculator can actually do that. But many of the calculators can't. See if your TI can do that. So you just type in 638.49 and hit the e to the x button. It has an error? Okay, excellent. Okay, so what do? Because I don't want my equilibrium constant in terms of e to the x. I want it in the power of 10. I want to kind of compare apples to apples when I'm looking at a table of equilibrium constants. So when your calculator gives you an error, this is what you do. So your algebraic skills are better than your calculator, believe it or not. So we have this situation. We have e to the y is equal to 10 to the x. And so how do we find the x? So here's one of the natural log, or any of the logarithm properties. If I have this natural log of 10 to the x, when you have two things multiplied by each other, you can change that to a sum of the logs of those numbers. So if I have 10 to the x, that's 10 multiplied by 10 x times. And so that would be x sums of log of the 10. So I can pull that x down. And so this is one of the properties where I can pull that x down in front. And now I have y and x in a constant. I know what this number is. I can take the natural log of 10. So I can solve for x, and that's y over the natural log of 10, or y over 2.303. So this is very handy. If I have e to the y, then that's equal to 10 to the y over 2.303. So this over here, I can make this substitution. That's pretty nice. And that allows me to write my equilibrium constant in terms of a power of 10. Now, what's funny is I don't do it anymore, but when I first played around with this, I took the 277, because I divided the 638 by 2.3 and 277, and I put 277, and then I hit 10 to the x. Well, if it couldn't do it in exponential space, it can't do it in 10 to the x space. So the log base 10 key, of course, gives an error as well. So your calculator just can't. It doesn't have a register big enough to hold that number. But my phone does. My phone will go, let's see, I think it gives an error on 800, but not 700. So somewhere between 700 and 800 it will go. And it ends up being like 10 to the 305 or something like that is the highest it will go. Now there's some other things that we can talk about in terms of the thermochemistry section. And one of them is coming up with delta H values, not using the table of thermodynamic quantities, but using group additivity. So this is just another way to come up with chemical properties. It doesn't have to be enthalpy. You can use group additivity for a number of things. There's group additivity tables for my solubility parameters. There's group additivity tables for lots of properties. And so what they do to make a group additivity table is they come up with these chemical groups. So like this might be 2 carbon atoms and 2 hydrogen atoms. And so this is a particular type of carbon. So this carbon here is different than this carbon here, where this one's bonded to 4 carbon atoms. And you see in this table, you have the groups defined, and then you have the pieces that kind of group would sort of donate or give to the whole molecule's delta H of formation. So you build the molecule and you break it into pieces. So like in this case, for hexane, we have 2 of the pieces that are methyl groups. Right? It's a carbon bonded to a carbon and bonded to 3 hydrogens. And so we go and find that in the table. So there's that piece in the table, and you multiply that piece times 2 because you have 2 methyls. And then you have this kind of group, which is a methylene group. Carbon here bonded to 2 carbons and bonded to 2 hydrogens. And you have 4 of those. So you have this one here, that one there, that one there, and that one there. So you have 4 of those type of groups. And so then it would be 4 times that piece. So these are the group additive numbers. You multiply by the number of groups you have, and then you end up with this number here. So 167 kilojoules per mole in the gas phase hexane. So the literature value is 198. So it's not great, but it's pretty close. And so then you might make this branched, and if you branch it, how does it change? Well, then you've got more methyl groups, and you've got a carbon that's one that has just 1 hydrogen and 3 carbons. So that's group additivity, just sort of showing you other ways that thermodynamics can be parsed out and that you can find numbers. There's also problems with it. It can't tell the difference between, say, chair and boat, or equatorial and axial forms. Then there's also quantitative structure property relationships, which you did a whole lab for. Okay. How many compounds did you end up doing in yours? Y'all had some freedom to do that. Do y'all remember?
40 something.
40. Okay. Was that about? Yeah. Maybe you added a few extra on your own or whatever, but it was around 40. Well, over several years, when sort of preparing that lab, I kept adding compounds, and I got up to over 900. So I have 905 compounds in my spreadsheet, and I went into the CRC and I grabbed the enthalpy of combustion for all of those compounds, and I made this chart. This is my QSPR. This is the results of my regression analysis, which is pretty cool. This is the performance chart for that. So here's the model, the QSAR or QSPR model, and then here's the literature values. And if it's a perfect match, it should have a 1 for a slope and an R squared of 1, right? So the intercept should be 0. I looked at it, didn't have a statistically significant intercept, so I set the intercept equal to 0, and it's pretty darn good. So the slope is close to 1, and the R squared is close to 1. And it's mainly because I have these really heavy compounds that really stretch it out and make a very good trend. Why is there so much spread down here? Well, look at the model. It's CA, HB, NC, OD. So here's A, B, C, and D. So all I need is the molecular formula to calculate the enthalpy of combustion. So it's a pretty crude model if you think about it, because it doesn't know the difference between, say, CH3, O, CH3, and CH3, CH2, OH. Same exact molecular formula, different molecule altogether, ether versus alcohol. And there's some slight difference in their enthalpies of combustion down here between those identically, the QSPR is going to give exactly the same number for both of those. So I've got one answer here, and I've got a range of answers here in terms of the literature values. So the more ways you can put that molecule together using the same number of carbon atoms, hydrogen, and so on, the more slop you're going to have in terms of your model. But, it's still a pretty tight range. No, I don't have, numbers off like this. And so that's a pretty good model. I've had a couple of students contribute to this paper to try to get it ready for publication, because I think this is somewhat useful for teaching the concept. I don't know, y'all went through the lab. I mean, did it kind of help you understand what you're doing? You have a structural piece, and you have a property that you're trying to model, and you have this relationship matrix. And we do that most easily demonstrated with molar mass, right? We have a molar mass, that's the property. We have the structure, carbon, hydrogen, oxygen, nitrogen, and the conversion relationship matrix is the individual masses of each atom. We did the same thing for the individual pieces of the enthalpy. Notice that you get more heat from carbon atoms than you do from hydrogen atoms. Nitrogen is kind of ambiguous because you have different types of nitrogen. Nitrogen's bonded to oxygens are sort of already combusted. The nitrogen's bonded to hydrogens may give you more energy. And so the positives and negatives kind of cancel out on the nitrogen number. But look at this number here, that's negative. So for every oxygen that you already have in your formula, you lose a lot of kilojoules. And that makes sense because you're reacting with oxygen. If I'm already reacting my fuel, then I don't have the energy density that I need, or have less energy density. This is why I'm really against putting ethanol in our fuel system. We're lowering the amount of energy per gallon because we're already putting oxygen in there. So anyway, this is the energy density, or specific heat, I should say. So by molar mass. So they really talk a lot about this here, that's hydrogen. So it's so light, and yet kilojoules per gram is huge for hydrogen. Okay, so you might hear politicians talk about the hydrogen economy. There's no hydrogen in our atmosphere. There's no hydrogen just running around. Hydrogen, we would store energy. We have to make hydrogen. So we could store it. You could use it as a storage medium, but it's not a primary fuel. This is like methane. So methane is probably the best of the hydrocarbons. These all kind of taper off. And then here's our energy density. So kilojoules per milliliter. And this is like a highly carbonaceous fuel, lots of carbon. These were your hydrocarbons, and down here you have all the oxides like alcohols, aldehydes, ketones, and acids.